Ah, darum machst du jetzt so viel, Alter. Besser ist.
Good, so okay, that's where we are. Yeah, so let's continue a little bit on this nonlinear optics stuff. There are more slides in your copies than I will go through, so the other ones, they are not essential for for the exam, but and sometimes I cover them, sometimes I don't. And you can look at them, some of them that is interesting, but I would like to finish this part today, so let's skip some of them. So here is our graph of nonlinear optical processes again, the simplest process frequency doubling. And remember, we said we want to image domains, so we need something spatially resolving, so we said optical techniques. And then I said it's also about symmetry breaking, Ferrari order. So we need a symmetry sensitive optical technique, and nonlinear optics is so much. So specifically with this process, if you look at that, you will find that this one, at least in the form it's written here, requires open central symmetry, otherwise it's not observed. You find a slide where this is, where the proof for this is written down, but for the moment I would just use that. So this is only permitted if you break central symmetry, inversion symmetry. So in that sense, it's very useful for imaging the emergence of ferroelectric order, because ferroelectric order breaks inversion symmetry. Yeah? You have this central symmetric situation, ion in the center. He moves off center, you get a polarization, and that's not central symmetric anymore. So right when this happens, when your material becomes ferroelectric, you have the emergence of such a frequency doubled signal. So it says SHE because second harmonic generation, it's on one of the slides, is also another word for optical frequency doubling. Good. So here you see the frequency doubled signal. And that's one of the big advantages of this technique. It's a higher order process, so it's frequency doubling, you need lasers and that stuff, so not much light. But it comes background free. So there's no light, and then there is light, so that means you just need a strong amplifier. So it would be difficult to say you have a lot of light and you now have a bit more. Then you have to separate much light from a little bit more light. Here it's less in the first place, but it comes background free. And that does not only work for ferroelectric order, it, for example, also can work for antiferromagnetic order. So if you take our chromium oxide again, down, up sequence of spins, that breaks inversion symmetry. Inversion would move the down spins from that side to that side, where there is an up spin, so violates inversion symmetry, and again, you get a frequency doubled signal background free from the magnetic order, from the onset of magnetic order. So then this is your experiment, this simple sketch. You send in omega light, sample doubles it, you block the omega light, and then you analyze the frequency double light. And because electric magnetic order break other symmetries, so they break different symmetries, and that usually corresponds to differently polarized light. So in the same sample, in the same experiment, you can even see electric and magnetic order in coexistence. Typically, the two contributions are differently polarized. So all you need is a polarization filter, and then you switch between detecting the electric or the magnetic order. So that's very convenient, and it also is a very robust process. So here you see the lithium niobate again, that you have seen a number of times. Orders at 1400 Kelvin, and when you measure the second harmonic intensity as function of temperature, you will see it exactly scales like the polarization. That means there is no, it really directly images the polarization of your sample. So you could say when you scan a range from 0 Kelvin, it actually goes down to 0 Kelvin to 1400 Kelvin, maybe that susceptibility also changes with temperature. This one, that one. It does, but only because of the changing polarization of your ferroelectric polarization of your sample. No other thermal effects, no nothing. So this is really a very pure picture of the polarization in your sample, the intensity of the second harmonic line, of this frequency double line. As you can see in this plot. So over more than 1,000 Kelvin, across more than 1,000 Kelvin. Here it says chi, so this substitutivity is constant except for the temperature dependence of the spontaneous polarization. So very nice technique therefore. This is then how it was used for the first time, so this nonlinear optical process to detect ferromagnetic order. Remember, ferromagnetism typically used this magneto-optical Kerr effect that I had on the earlier slide, but this frequency doubling technique can also do it. So you take a ferromagnetic iron surface, minus or plus magnetize it in a magnetic field, and then you see that the emission intensity of the frequency double light is a little bit different from plus and minus M. So it's very noisy, but the average clearly is different. And that difference goes away when you oxidize your surface, so that the magnetization is gone. So you have a background contribution from the surface, and this splitting here, this is all due to the magnetization. So that was about the first time, not the very first experiment, it was the first very convincing experiment in 1991 where they showed that frequency doubling can see magnetism. That's not so obvious because remember, photons do not interact with spins. So you need some process that goes in between the spins and the optics. Any idea what that could be? A process that you know. What connects magnetization, spin, light? Spin-orbit interaction. So you cannot see spins, but you can see orbital moments and spin-orbit interaction. So the magnetization, the spins couple to the orbital contribution, and that orbital contribution you can measure with this process. And this is one of these typical experiments that was too early to be successful. So they showed something really nice. So they grew a sample, they grew a nickel film, a ferromagnetic nickel film. And while it was growing in that chamber, they measured the frequency doubled emission. So they measured the second harmonic intensity. So they could see 0, 2, 4, 6 monolayers, and they measured it in a magnetic field, so they measured it for magnetization up and down. And then they could see here 5.5 monolayers, you suddenly get a magnetization dependent splitting in the single intensity. So this is when the sample actually gets ferromagnetic. That's a very important question when you go work with thin films. When actually does the order happen? And here they see it while they grow. So here, 5th monolayer, it gets ferromagnetic. Then suddenly it's gone again, and now it shows up in a differently polarized contribution of your signal line. So here the magnetization changes direction. So you can track what is happening in your sample while you grow it. So you can exactly react to that and improve the process or avoid something you don't want. So a breakthrough experiment in 1999, published in the small journal and forgotten. And now this is really used for devices here to monitor how do samples develop their magnetic electric properties while you grow them. That then explains why can you see antiferromagnetism with light. So I'm referring to this experiment that I showed earlier on. So you can calculate how would the intensity of this frequency double light depend on your antiferromagnetic order, which goes plus minus or minus plus in the different domain states. And then you find that there is a frequency double contribution that is background, and one that depends on the sign of your antiferromagnetic order. So this one or that one. And also depends on the sign of the circularly polarized light. So it says here. So that means you measure 2 spectra for plus and minus circularly polarized light. And then you go to a different spot on the sample, you measure exactly the same spectra but with a reverse polarization dependence. And that's exactly what you have here. So you reverse your polarization dependence, you get a different intensity. That's what you should see here. Or you reverse your antiferromagnetic order, and you also get the same change, and that's what you see here. So you go from red to red here, or from blue to blue there. And when you change both the circular polarization and the antiferromagnetic domain state, nothing changes. That's why the spectra look the same. You go from red here to blue there, or from blue there to red there. So when you change both, you get the same spectrum. So this is very, very strong prediction. So if you really see that in a sample, then it's very unlikely that there's another explanation. So that was then a demonstration that you can really see antiferromagnetic order with a very large contrast between the domains. So look at the contrast that you have. So from right here to right there. Very large contrast between the domains. And then you can just say, okay, I now take light at this photon energy, so 2.1 electron volt, that's orange light. And I image my sample in this frequency double light. And then I would get a lot of light from one domain state and no light from the other. And that's what you see here. Yeah? And when I turn my circular polarization around, I see no light from one and a lot of light from the other. That's the change from here to there. So right-handed circularly polarized, left-handed circularly polarized. And when you are above the ordering temperature, you only have the background contribution. That one is set down. So that is also kind of breakthrough because now you have an easy method to image antiferromagnetic domains. So not polarized neutrons for 24 hours, but a little bit of light for like a minute. So that was quite important. Then the next issue on our list, so this was about imaging techniques. Now, something that became quite important recently is domain walls. So the region of transition between different orientations of the order parameters. And they can have any width, so 1 unit cell to like 1,000 unit cells or micrometers. So everything's possible, again, depending on many parameters that enter this. And then there's one fundamental difference between magnetic and electric domain walls. So you cannot reduce the spin to zero. So spin is quantized. That means when you have one spin orientation in one domain and another spin orientation in another domain, the only way to get from one to the other is to rotate it. So either like this or like this. That's different for ferroelectric domains. There you can simply reduce your dipole moment to zero. It's not quantized and reverse it. Also in domain walls you get new physical effects because the symmetry is lower, and this is why they, for about 15 years, are now attracting a lot of attention. So people think about domain walls. On a surface there are lines, so they say we can make electrical circuits using not like metal connections between the electronic elements, but domain walls. The advantage is you can never rewrite a metallic channel between circuit elements, but you can rewrite domain walls. So you have rewritable electric circuits made by domain walls. So this is why that topic is now quite important. Here you see what I've just said. So when you have the change, the reversal of a magnetization, it can go like this, or it can go like that. And depending on what it does, it is called Neowolf or Bloch-Wall. In contrast, for the electric domain walls, ferroelectric domain walls, you do not have quantized spins, so you can reduce your electric polarization, your dipole moment to zero, and then it reverses coming out at the other side. That is called Ising-Wall. And although you have these three, you can also have mixed situations, like a mixed Ising-Mehl wall. So here the polarization gets smaller, but it also rotates. So all that is possible. Here's the experiment that shows that you can actually have this mixed Ising-Mehl wall character. So you can image these domain walls. with this frequency doubling technique that I just introduced, and you can also do transition electron microscopy, and then you can see how the atoms are displaced and they rotate. This displacement rotates and shrinks at the same time. So this is mixed female male character. Here in a lead zirconate native on a specific substrate. Good. Then how thick are these walls? I just mentioned that they can have any thickness between a nanometer and a unit cell and 1,000 unit cells. Yeah, that depends a lot on the conditions you are in. So if you take magnetic domain walls, for example, you have typically a competition between exchange energy and anisotropy energy. So exchange wants to keep your spins parallel. So it wants very wide domain walls, because if they are very wide, then the side-to-side rotation of your magnetic moment is very little. And your spins are largely parallel all the time. On the other hand, anisotropy energy doesn't want spins to point into other directions. So that would favor very narrow domain walls, because it hates this. So it would not tolerate a lot of this. So it would just say, okay, one domain, then immediately boom. And anisotropy wants narrow domain walls, exchange wants wide domain walls. Okay, you add them up, you minimize, and then you get a certain wall width as a compromise. And for ferromagnetic domain walls, it's typically like 10, 100 nanometers, very rough. Yeah, 100 nanometers. For ferroelectric domain walls, it's different. You don't have any exchange energy. Yeah, you have anisotropy. This is not quite true. You have no exchange contribution, but you can have anisotropy. So I have to correct that. So no exchange contributions for ferroelectrics. Anisotropy is there. So that doesn't belong there. So cross it out. But then you have dipole-dipole interaction, gradient effects, and many other effects. So that in total they tend to be very narrow. So it's even that you have anisotropy energy, so that wants narrow walls, and therefore ferroelectric walls, for that and other reasons, are typically very narrow. One unit cell or a few units cells. Unless you have improper ferroelectric order, because then the material is primarily not ferroelectric, it's only a side effect that it's ferroelectric, but something else dominates the wall width. So if you have magnetically induced ferroelectricity, then you have to look at them as magnetic domain walls, and then they describe these processes by the ferroelectricity. Then, how do you actually change whole a material? So how do your domain walls behave? So you would say, if I have like a plus magnetized sample and then I want to reverse the magnetization, then I apply a strong magnetic field, or the other way around. So I have down magnetization, I apply strong magnetic field. Okay, then your sample switches. Your spins switch everywhere, they go above this well, and then they drop into the other potential well, potential minimum. But that typically doesn't happen because it costs way too much energy. So you usually pole a sample by domain wall movement. So by making one domain state larger in terms of domain size and the other one smaller. So you have shifting around domain walls rather than a real flip of your magnetization. So the solution is easy because you can see it with this analogy with card games. So you probably have seen in the movies, or should you gamble that you have also seen it. You reverse a deck of cards, and then you know that these guys are really very talented with that. So then they flip across the deck of cards, and they flip the feet back and forth. So it always has the same shape, but it always involves different cards. So such kind of phenomenon is called soliton. It keeps its shape. It's also a mathematical topological object. It keeps its shape, but always involves different cards. It's also like a water wave. The water wave travels, but it's not the water molecules that travel. It's only the wave that travels, and the individual, it's always carried by different water molecules. It's not water moving. And that's the same. So that costs very little energy. So you have a reversal. So here it's all down, say, or all back, all front, but it almost didn't cost you any energy to do this. You just have to slide around this peak. Whereas that complete flip, taking your deck of cards and really turning it around, that would have cost a lot of energy. So this is how you polarize a sample. You move the domain walls around. You have to nucleate them at first before you move them around, and that typically happens at little defects where they are easily created, so that you do not have this initial situation that you have to come across with. Yeah, so they behave as a wave packet. The domain wall always looks the same, but it always involves different atoms in the material, and then they can go around. Then I mentioned that domain walls are studied a lot at the moment because they have properties that the material itself does not have. For example, and that's mostly due to the lower symmetry that the domain wall has. So here, for example, magnetization is all up, and then here it suddenly points into some odd direction. So here the symmetry is lower, because here you would say you have a rotational symmetry around that axis. Here that's gone. If you rotate around that axis, then that is not a symmetry proportion anymore. So domain walls have lower symmetry, and because of that, they can carry effects that the bulk cannot carry. For example, an antiferromagnetic wall, domain wall, can carry a local magnetization. A ferroelectric domain wall can carry local strain. And then you can work with that. Because the lower symmetry, it could also, one consequence could be a local magnetization, which is nice, or maybe they conduct the electric current better. And then you are back to this idea that I mentioned before, that domain walls could be like conducting wires. So that is something that is now studied a lot. Here is an example for a domain wall carrying a drastically different materials property compared to the surrounding bulk. Tungsten oxide, which is ferromagnetic or antiferromagnetic, I don't even know that. Well, it's magnetically ordered. I can add that. But what you see is that at the domain walls it becomes superconducting. So your electrical resistance goes to zero at some temperature. That's very interesting. Huh? So you have bulk material is like a normal conductor, so it has electrical resistance. But at least below 2 Kelvin, suddenly, in the magnetic field, suddenly you have, 0 Tesla. So at 2.5 Kelvin, suddenly the walls become infinitely conducting. So imagine that. You have an electric circuit, and it's not wires connecting the elements, but superconducting channels that you can even rewrite, because you can pole your material. That is something that people find very interesting. So this is understood, so it's something with chemistry, and it's and superconductivity and local inhomogeneity. So it's a complex effect, and I'm not going to discuss it. I'm just indicating here it's understood why a material does look like that. Yeah, and here you see ferroelectric domain walls. It's an emerging field, so I would say there was one paper in 2009 that more or less kicked it off. Those are more recent, so like 20s. Now you see these are reviews, and then ferroelectric domain walls for nanotechnology. Ferroelectricity plays a lot of a role, and then if the materials magnetize and polarize at the same time, you get even more interesting effects. Generally, they all play on the same. So you have a wall, or in ferroelectrics, you have So I'm specifically talking about a ferroelectric domain wall. So it's always the same. If you have a ferroelectric wall, it's strained. Here, look at that. A wall always carries lattice deformation, meaning strain. Ferroelectric wall. So you have strain. Strain induces defects in your material. Defects attract charges, and you can screen polarization or enhance it. Then you get electronic band deformations because of the electric field built into your material. And that somehow ends up bending, so gaps become smaller, or you slide around the Fermi energy, so that in the end they have a different conduction, electrical conduction. But that gets you from the ferroelectric walls to conducting wires. just what I just mentioned. So this is researched a lot right now. Remember, the big difference to conventional electric circuit boards is that these are movable wires, so rewritable wires. So that is the big chance. This is the experiment that kicked it all off in 2009. Bismuth ferrite, which is a ferroelectric material, and then they did conducting atomic force microscopy. Now you know what that is. So they moved the tip across the surface and they measured the electrical current going from the tip through the sample and into a back electrode. And then they measured where there are domain walls, you suddenly have a lot more conduction. Here shown by the brighter region. So that was the paper when they realized, oh yeah, they can be like wires. They even made a conceptual demonstration of this wire principle. So they had two metallic plates here. Strontium mucinate is metallic. And in between they have bismuth ferrite. And then they, with their tip, with their voltage tip, with the voltage that they locally applied, they created an oppositely polarized bismuth ferrite domain. And that means they created two walls, two ferroelectric domain walls, going between the two electrodes, because this goes through the entire material. And then they could show that if you have zero of these wires, so you don't have this oppositely polarized domain, then you get this curve. So voltage, current voltage dependence. If you have two wires, then you get here two, you get the blue one, so it conducts much better. And here you see the principle 0, 2, 4, 6 walls as conducting elements going between the electrodes, and the one with the largest number of domain walls is also the best conductor. Even if they erase, that's the principle. Right? You can erase wires again, so you can go back from 6 to 4. And then you see you get to the green line and it's exactly as before. So 4 wires going between the electrodes and getting this intermediate conductance. So this is 2009, you would say now 15 years, so they did a lot more than that. Yes, they did, but we still don't, we are not, I mean, you can still not buy this kind of stuff at Bauer. So it's still in development, still basic research, but it's a very active field. Here's another one where you can see domain walls, and depending on the direction of the ferroelectric domain wall, you can have lower or higher conductance in the wall. So this is even more intricate. It's not only that the wall can be a conductor, a wall can also be a conductor depending on the orientation of the wall, which is another interesting functionality you can play with. It's this hexagonal manganese pattern, which is interesting because you remember it was this topological pattern where 6 ferroelectric domains always meet in one point. And that's the power of topology. So that mathematics guides your domain formation. I told you normally head-on domains where polarization meets head-on or tail-on. Materials don't like that. So they don't want that. But in this kind of ferroelectric, you must have it because you somehow need to connect this domain meeting point to that one. That means there must be a region where you have this head-on situation. Mathematics wants it like that, so you cannot avoid it. That's the power of topological effects, topological ferroelectricity. You can force it into a state that in terms of nature it would normally avoid. So what does it do when this happens? You move screening charges here, or you take them away. And then you get exactly this. So if you move screening charges away, conduction goes down. If you move screening charges here, conduction goes up. So that's what this paper was about. What is this? Yeah. So then this guy here, Dennis Meyer, he pushed it even further. So he was still first author, then he went to the lab himself and did the stuff. And in this next one, he was the group leader. So then you are the last author typically, and he showed that not only you can tune your conductance of your domain wall depending on its orientation. You can also build circuits where it is a rectifier. That means it converts an AC current into a DC current simply by chopping off the negative end. So that means you would only have conductance in your domain walls for a certain polarization direction, but not for the opposite one. That means if you send in an AC input voltage, what comes out is this part is killed because there the conductance of the domain wall is high. That one survives, and that means now your current is flowing in one direction but not the other. So you convert, under losses of course, you convert AC into DC effects. So and that's what is rectification. With the same material. Yeah? So it's this, you need these unfavorable parts in your sample where polarization meets head or tail on. So you are bound to need to this topological ferroelectric for this kind of experiment. Okay, so that then is exactly, so wait a minute. Ah, very good, yeah, I'm exactly in time. So that shows, someone asked before in the break, yeah, so is the thickness of a film, isn't it also important how some ferroic order behaves or develops? And yeah, that's true. So for example, ferroelectric films, the domains are the smaller, the thinner the film is. That's also understood, but here we just use the result. So there is a relation between the width of the domain and the film thickness. And because of field energy contributions and other effects, you then get smaller domains for thinner films. That is a relation that holds over many, many orders of magnitude in film thickness. So logarithm of film thickness, so here it's just 1 nanometer, so almost down to 1 atom, and here it's 1,000,000 nanometers, so basically a millimeter. Many orders of magnitude, and you have the scaling or variation in the domain size. Another functional aspect to work with. Good. Then a very particular one, so that is concluding today's lecture. So where we get back to this relation between nonlinear optics and ferroic order. So when you grow a film, magnetic or electric, then you would like to see that it grows nicely. So atomic layer by atomic layer, so not just a heap of atoms, or not just a mountain region, but you really want flat films. Atomic layer by atomic layer. So when you grow your film in a chamber, you have a tool to monitor that. So that's a typical thin film growth chamber. So you have a substrate, then you have a target of some material. You want to grow a film of that material. So what do? You hit it with a very strong light beam. So then you basically sputter off material of your target. You hit it with such a strong light beam that you basically, it's like you shoot at it with a pepper gun, and then material spatters off. And that material then flies through vacuum and then deposits partly on this substrate here and forms a neat film. So atomic fragments are shot off from this target, they fly through the vacuum, and they condense down on this substrate. And if you do it under the right conditions, then it's not just stains that you get, but you really can make it that these atomic fragments arrange themselves into neat atomically crystallographic like atomic patterns. Atomic layer by atomic layer. So that technique is called pulse laser deposition. Again, he's the expert in that. And yeah. So then you need the tool to tell you, yeah, I'm growing a neat film. And that is typically that you use electrons. So you have an electron gun. Electrons are reflected off this glowing thin film, and then you can see if it's a sharp reflex of your electrons, a diffraction reflex. Then you say, okay, it's nicely growing atomic layer by atomic layer. And if that goes away, then you know something is wrong with my film. Okay, then you know that you have a nicely grown film, but you do not know if it does what you want it to do. So in the end, you don't grow a film because you want to grow film. You grow a film because you want it to be ferroelectric. So how do you see that? So how do I see while I grow that my film is actually getting ferroelectric? Yeah, I can see that it grows nicely, but it doesn't mean that it also is a nice ferroelectric. That I do not see with electrons. So what you can do is you can then go back to what we have seen today. You can say, okay, I also send in a laser beam, and I look at the frequency double light. And if there's frequency double light, then I can assume, for example, it gets ferroelectric. Now remember, ferroelectricity breaks inversion symmetry and switches on this light conversion. So that's what you do. You send in a laser beam onto your target while you grow it, onto your film while you grow it. You measure the frequency double intensity, and then when it is there, you know, oh, my film gets ferroelectric. So that's something that you can do, and we have the setup, so we have, and it's basically the only one you find on this planet, and therefore in the universe. To monitor thin film properties emerge while you grow. In buried states. So here you see what would you do if you don't have this. You would grow thin film up to some thickness, then you would just stop the growth, take it out of your chamber and measure if it's ferroelectric. Then you would do it at a different thickness, 10 unit cells, 20, 75. And then you would see, yeah, it's always ferroelectric, so probably the ferroelectricity then sets in somewhere before 5 unit cells, and if you would take 2 unit cells, maybe the ferroelectricity is gone. That would cost you 1 day per sample. And it's indirect, because you measure 4 different samples and you measure them after you have grown it. 4 data points, 4 days. Now we take this setup, we measure while we grow. Now you get 100 data points in 20 minutes. So here you see, while you grow a bismuth ferrite film, this frequency double signal, and it stays 0 until you have 3 monolayers, 3 atomic layers. Then the signal comes about, increases, and after the 10th monolayer, so 10 atomic layers, it behaves like a barcode signal. That's immensely powerful, because now you can really track what is going on during my growth, and you can counteract it. And remember that early experiment from the 90s where I said they did this for a ferromagnet. You remember? Yeah, that I showed it earlier on. So that was forgotten in those days, but with this one you pick that idea up and you track magnetism, polarization, whatever, while you grow your sample. And that even tells you processes going on during your growth that you can never find out if you characterize your film after you have grown it. So for example, here you grow a lead titanate ferroelectric film, and then you see what I've just seen. So it gets ferroelectric, so film gets thicker, so you get more of this ferroelectric frequency double signal. But then at some point, for a certain thickness, your signal goes down again. So the frequency double signal goes down. So somehow polarization is disappearing. Until then, from 20 nanometers, it's increasing again. And what that tells you is you grow with an out-of-plane polarization, that titanate, and that makes this signal. At some point, the polarization flips into the plane. So you lose contribution to your out-of-plane polarized signal, you really lose it, so it goes away. Until this multi-domain situation stabilizes, and then the entire thing grows in thickness again. You would never be able to see that after the growth. You would just see, oh, I have a sample with multiple domains, I don't want that. When did that happen? Here you see when it happened, in the years. And then you can do something here to prevent that. So that's the power of this kind of in situ monitoring of your sample growth. More on that again in his lecture. What is nice here is that this is then actually now, so in the 90s it was an experiment that was essentially overlooked. Then this was picked up again, demonstrated on many ferroelectric films, converted from a big lab laser into a small device, and now there's a company selling this. So if you're still in search of Christmas presents, that's the thing. It even makes a great doorstop, so or fancy. Yeah, okay. Anyway, so this is where then actually academia, so university research, basic research, eventually reaches the market, and that's what material science is about. To make use of properties and convert them into something you can work with, and not necessarily only for basic research purposes. So that's one way of how it could go. Good. That brings me to the end of today's lecture. Now I'm in 5 minutes early. More, okay, no problem. So I put it on my account, and next time I will check it probably longer. Or maybe you have questions? Want a prize for this? Can give you a very good prize. I know the company owners. Okay. If not, then we are done for today. And I think next week it's either me or Professor Simon. I don't know yet, but you will see. Good.
Yes, spin-off from Dragon.
Sie bleiben. Ja. Wunderbar.
Wie versprochen.
Finde ich super.
Okay. Look, kann man rein? Sie in der Mitte fast.
Und jetzt wirklich geil, jetzt bin ich auf dem Fotoboden.
Ja,
Der Bus außer mir.